Good day, students. Welcome to part two on the installment of finding the gradient of scalar functions. Let's go ahead and take a look at an example. So these are the instructions for the example. It says find the gradient of f, or also known as del f, at the given point and state what your result means. All right. So the second example that we're going to be considering in this um, example is as follows. So we're going to be looking at the function. Uh, this is example two. Example two, we're going to be looking at the function f of x, y, z equals negative x squared minus y squared plus z plus 3. And then we're going to be looking for the gradient at the point 1 comma 1 comma negative 1. Okay, there's a link that you can click down here to look at the example for part 1. It's similar to this. In that case, we looked at the sphere of radius 3, and in this case we're going to be looking at a paraboloid that's shifted 3 units up. Okay, so let's take a look at this example. We're going to find the gradient first. I'll do the mechanics of computing the gradient using partial derivatives, and then we're going to write down what the solution of our result actually means. All right, so let's go ahead and find the gradient first. So the gradient of f is also written as del f. Del is a vector operator. It, uh, it can act on a function, or it can be crossed or dotted with a vector. So upside down delta of f is the way you depict a gradient of a function f, all right? And the formula for finding, or the procedure for finding the gradient, or del of f, is to take the partial in all three directions, and then you put the vector components in there. So del f is partial f with respect to x in the I direction, I hat, plus the partial of f with respect to y in the j direction, j hat, plus the partial of f with respect to z in the k direction, k hat. All right, so that's what we're going to be doing in this example. So the del of this particular example, del of f, what we're going to do is we're going to be taking a partial with respect to x of this whole story right here, which is negative x squared minus y squared plus z plus 3. That's going to be in the I direction, plus the partial with respect to y of the same function, negative x squared minus y squared plus z plus 3. That goes in the j direction, and then the partial with respect to z of the same function, negative x squared uh, minus negative x squared uh, minus y squared plus z plus 3. And that goes in the k direction, ijk. All right, these are vectors. All right, so let's go ahead and compute the partial derivatives of this function in all three directions. So Uh, since we're differentiating with respect to x, the partial derivative of x, everything else other than x will be treated as a constant. All right, so if I apply the power rule for derivatives in negative x squared, I'm going to end up with negative 2x, and then partial x cancels out, so you're just left with negative 2x, and that's in the I direction. Partial respect to y, everything else becomes a constant except negative y squared, so if I differentiate negative y squared is in the power rule. It's gonna be negative 2y. So it's gonna be minus 2y. Partial y cancels out, so this is what you're going to be having in the j direction. And then plus partial respect to z. Everything else is a constant. Using the power rule here, you're just going to have 1 in the k direction. All right. So this is basically your del of f. Del of f is negative 2x in the I direction minus 2y in the j direction plus k. All right, I don't need to put the 1 there. All right, so we're asked to find the gradient of this function at a particular point. So what point is it? This 1, 1, negative 1, right? So we're going to compute the gradient of f at the point 1, 1, negative 1. So this vector valued function right here tells you how to find the gradient at any point on the surface that we have. Okay, so at this particular point, what is the gradient going to be? All you just have to do is just plug in the respective coordinates into the slots here, and that will tell you what it is. All right, so we're going to have negative 2 for x. We're going to put in 1 times 1 in the I direction minus 2 times 1 in the y direction. It's j, and then it's independent of k. All right, so I'll just put the k there. All right, if I simplify this, my gradient is going to be negative 2i minus 2j plus k. Okay, so that is the answer that we're looking for. All right, so let's box that. That's the del f at negative 1, 1. I mean at 1, 1, and negative 1. All right, so now let's write down the meaning. What on earth does this result we just arrived at mean? All right, so the meaning. We're going to consider in the context of ascent and descent. So we're going to look at ascent first. All right. So what does this mean in the context of ascending? All right. So under under ascent, um, what does this function mean? Well, it means that the direction of quickest ascent. You know what ascent basically means you're going up the function, right? Going up the surface, sorry. The direction of quickest ascent of the function, which is a paraboloid in this case, of the function f is the direction, the direction, the vector del f, which is equal to negative 2i minus 2j plus k points. Okay? So wherever direction this vector points, that's the direction you want to go to if you want to ascend to the top of this uh, function at the quickest rate. All right? So another thing to note is the rate of the ascent. So the rate of ascent um, in this direction, which is the quickest ascent, is given by the magnitude of the gradient, the magnitude of del f, and the magnitude of del f is simply um, the magnitude of the vector. So it's basically the square root of the sum of the squares. So the square root of negative 2 square plus negative 2 square plus 1, which is the square root of 4 plus 4 plus 1, which is root 9, and that's 3. All right. So this is the rate of ascent along this direction. All right. So that's if you want to ascend to the top of the function. What if you wanted to descend to the base of the function? What on earth does our answer mean? So let's consider the meaning of our answer in the context of descent. You're going down this function from the points 1, 1, and negative 1. What our result means is that um, the direction, the direction of quickest descent, okay, of the function, which is a parabola in this case, paraboloid, sorry, of the function f is the direction is the direction that the vector negative. We're now going to do the opposite of del f. Since del f ascends quickest, the opposite of del f will go down, will descend the quickest. All right, so all that means is you just distribute minus to all these vector components. So you're going to have negative del f equals 2I plus 2j minus k. Okay, you see here the positive k means you're going up, and then this one negative k means it's like a downward pointing vector. All right, so is the direction that the opposite negative del f, which is 2I 2j minus k points. So if you want to get to the base of this function at the quickest rate, uh, you just go in the direction of this vector, okay? And the rate of descent, the rate of descent in this direction, is given by the opposite of the magnitude of the gradient of the function. Okay, we know that the gradient of the function was the magnitude of the gradient of the function was 3, right? So the opposite of that is simply negative 3. So this is your rate of descent in that direction. All right. Okay, so let's look at a visualization about the result that we just generated and see if we can have a deeper conceptual understanding of our result. Okay. So I have a 3D space right here, a 3D graph, and what I'm going to do is I'm going to put the plot that we just generated here, right? So this is your z-axis, there goes your y, and there goes your x. So I'm going to sketch the graph of the paraboloid I just generated using this computer program. So there goes your graph, all right? So you have a nice paraboloid right there. So what direction does the gradient point? At any particular point, if you want to find the direction that the gradient points, all you just need to do is you just draw a plane tangent to the surface at that point, okay? A plane to the tangent, if you draw that plane, the normal to that plane will give you the direction that the gradient points in, all right? So all we just need is a tangent plane and then a normal to that tangent plane, and that tells me the direction that it points, the gradient points, okay? So we're looking at 1, negative 1, I mean 1, 1, negative 1, so we're going to come out, and then negative 1. So somewhere down here should be where our tangent plane should be drawn, all right? So I'm going to go ahead and draw the tangent plane. Bam, so you have it somewhere down there. All right, so if you look at it, you see that the plane is tangent to my paraboloid, to my surface at that point. Okay, so if I want to draw the if I want to draw the gradient, the gradient is going to be pointing inward in this case. Remember the result we have negative 2I. That means you're going in the direction of decreasing x. Negative 2j means you're going in the direction of decreasing y. So the vector should be pointing inward. All right. So there you have it. All right. So this vector right, this line right here, this vector is tangent to this plane. Let me take the graph off so you can see. It's perpendicular 90 degrees to this plane, all right? To the tangent plane to the surface, all right? And this is the direction of quickest ascent. This is the gradient of the function, all right? If you look at it, you notice that it lines up perfectly with your z-axis, all right? And it takes you to the top. Wherever the top of this surface is, this direction points in the top, in the direction that will take you to the top at the quickest rate. All right. So what if you wanted to descend? This is the point right here we're looking at. What if you wanted to descend to the bottom of this paraboloid at the quickest rate? What direction would you point? What's the direction of the quickest descent? It's going to be the opposite of this vector right here, which is tangent to the surface but points in the other direction. And there you have it. So this is negative del f, and this is del of f right there. All right. So these basically help you see the 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 uh, the graphical component of what we just computed. All right. So what we're going to do is extract this to our worksheet, and then I'm going to label it so you can see the connection between the results we just generated and and this graph I just created. All right, so there you have the surface that I generated. I've just captured it into my editing program. So what I'm going to do is I'm going to label this graph so you can really understand what we're dealing with. Okay, so this surface right here is the function. Okay, this is f of x, y, z equals, as a paraboloid, is equal to negative x squared minus y squared plus z plus 3. Okay. Um, And this point right here, that point where that's the plane is tangent to the surface, is the point 1, 1, comma, negative 1. All right. Uh, so this plane right here is known as, we can call this the normal, normal plane. I mean the tangent plane. Sorry, tangent plane to the surface. So tangent plane to F at 1, 1, negative 1. All right. So this is the tangent plane. So the line, see this line right here? If I drew a line along this tangent plane through this point of intersection downwards like this, along this plane, the angle between this line and this vector right here that's normal to the plane is going to be 90 degrees. So this angle is 90 degrees right here. Let me just put it in. So this angle right here is 90 degrees. All right, 90 degrees. What is the significance of this vector? This vector right here, this vector that's normal to this plane, is known as the del of f. So this vector right here, put it over here, normal vector, normal to the plane. So the vector normal to the plane pointing in the direction of increasing y, increasing z is del f. Okay, this is the del f that we found, and del f was basically 2i plus 2j minus k. All right. So that is how you find your gradient. So any point, you just draw a tangent plane, and the normal line in the direction of increasing z will be your gradient of the function. All right. And then this line that points in the other direction, this is the opposite. This is the opposite of del f. Okay. And that one is negative 2i minus 2j. Oh gosh, negative 2i, negative 2i minus 2j plus k. All right. And then this one is the quickest descent. If you want to go to the bottom at the quickest rate, this vector points in that direction. And then this vector right here is for ascending. If you want to get to the top of the function at the quickest rate, then this vector right here will help you get to the top quickest. Okay, so this is I and this is J. I think my I and J is confused. All right. So there you have it. All right, thanks so much for paying attention to this presentation. Please subscribe to my videos so they can get future updates and share with your friends. If you like this video, you can click down here to like. If you didn't like it, you can post a comment or send an email, and I'll be glad to address your concerns in this video or subsequent ones. For a collection of more clips, you can visit my site at mattgoodserve.com. Thanks again and have a wonderful day.